Hi everyone. So in this video, essentially be going through the solutions to the Bayesian model update task that is given to you in the assignment. So without further ado, let us now proceed to go through the first task. In task 1a, we're instructed to set up the nominal Hooke's law model for the linear static spring mass system. So as you can see, this is actually quite straightforward in doing. You just need to define the function handle, and you just give, of course, a name for the model, which I call it model nominal. And from there, you just initiate an empty table so that the results can be stored in. And you then just define the model in accordance to the Hooke's law equation, which is force equals to negative k stiffness multiplied by d displacement. And this is just simply the output of the model. So with that, we'll now proceed to task 1b, whereby we're supposed to set up the noisy Hooke's law model for the linear static spring mass system. Now, as you can see, this is very similar to task 1a, with the exception of, firstly, the need to assign a different name to the model, which in this case for the noisy Hooke's law model, I just simply call it model for short, but of course, having said that, you can always assign it a different name. Just need to make sure that you know that it's referring to the noisy model. And you just input the same mathematical definition, with the exception of the last line, where you can see that the output includes an additional perturbation term. This is essentially the epsilon, the noise term that follows that Gaussian distribution. So as you can see, that there's not much difference, and it's pretty straightforward as well. So with that, let's proceed to task 2, where we are instructed to prepare and define all the parameters and random variables to be used in this setup. In task 2a, we are to define the parameters using the parameter constructor from OpenCosine. So first, we are to define the true stiffness parameter k using the OpenCosine parameter constructor, and this can be done by as follows. So in this case, I just assign this parameter as stiffness real, and as mentioned in the assignment, this is assigned a value of 263 newtons per meter. You can do the same thing for the displacement, and just use the parameter constructor to assign it a value of 0.05. Following which, you are to actually assign to define the noise random variable for the noisy function, and I just call it noise standard deviation. And you are supposed to use the random variable constructor for the normal distribution to do so. And essentially, all you just need to do is as follows. You just use the normal random variable constructor, setting mean 0 and standard deviation 1.0. And in the description, you can just put anything you want just to denote that this is the noise standard deviation that's assigned. Following which, we have to consolidate the random data using the OpenCosine random variable set constructor. And this is done as follows. Just use the random variable set constructor, and you just need to make sure that all the random variables are being consolidated in here. And following which, we proceed to task 2b, where we are instructed to simulate the perturbed data of the noisy force measurements. So in the first subtask, you are to consolidate the input parameters and random variables for the noisy model using the OpenCosine input constructor. And this is done as follows, as in line 40. I just call it x input perturb, and just use the input constructor as follows. And you need to define essentially the members. So this is our stiffness real, displacement, and all the random variable set that you previously defined in the previous subtask 2a. And just make use of the corresponding member's name. And these names, just make sure that they go in order, the same order as what you do for the members. And then if you want, you can actually add this line to display the input in the command window. And the next step, we have to prepare the noisy model function to handle the OpenCosine using the OpenCosine Meyer constructor. And this is done as follows. You just use I just call this x Meyer perturb, and you just write in this this line, which is the Maya constructor, and you just call out the noisy function, which we previously called it model, and you just make sure that this is correctly used, and just define the relevant input names, or the inputs that are required for the model: stiffness, displacement, and noise standard deviation, and the output names y, because we call it y, and format table, and there you go. This is that's all there is. And following which, you have to add the Maya constructor to the evaluator constructor from OpenCosine. Now this is done as follows. You just I just call it X evaluator perturb, or you can give it any name you want, and just use the evaluator constructor as such, and just define the members X Maya perturb, which is essentially that noisy function that you just prepared, and give it its respective name. And from there, you can then define the noisy model using the model constructor from OpenCosine. And this is simply as follows. You just add this line, OpenCosine common model, and just define the inputs and the evaluator using this that you defined in the previous subtask. And from which you can there prepare the multicolor constructor from OpenCosine. So we mentioned that we want to generate 500 samples, so you can just define your sample size, and you prepare the multicolor using this constructor, OpenCosine simulations multicolor, and n samples being whatever sample size that you wish to simulate. And from there, you can then perform the multicolor simulation using the apply method, and it's essentially just you doing this at the apply class and to the perturb model, and there you go. And from there, after you perform the simulation, you can actually display the resulting outputs, and using this get values class, and you just simply define the output that you wish to extract from there. Now that concludes task 2. Now task 3, we have to perform deterministic analysis, and this task actually in most part similar to what you did in task 2. So in the first part, we have to consolidate the input parameters and random variables for the nominal model using the input constructor. So in the same fashion as we did in the second subtask, you actually just make use of the same input constructor, and you just put in the same input members, because they were working on the model that actually uses these two input parameters. And then in the deterministic analysis, we prepared the nominal function handle instead of the noisy function handle. So that's the only difference. So making use of the Maya constructor in the same fashion, we just input using this line, except that now instead of using the model, I use the nominal model, which I call it model nominal, and just do the same thing as you did in the previous task. And from there, you just add the Maya constructor to the evaluator constructor from OpenCosine using this statement, and from there you just define a nominal model using the model constructor from OpenCosine, as you can see over here. And following which, you can then perform and execute the deterministic analysis, and this is done using the deterministic analysis class, and you just act on the nominal model that you define in this line over here. And from there, you can yield the actual true value of f by getting this, making use of this get values class onto the output. And in order to check that you're on the right path, this should actually just yield negative 13.15 if I'm not mistaken. So this in essence would be one way to check that your code is actually running correctly. So with that concludes task 3. Now in task 4, we have to actually perform the Bayesian model updating analysis. So in task 4a, we have to define the prior and the likelihood functions. So we first start off by defining the prior random variable. So the prior is actually a uniform distribution. So what I did was that I actually defined the lower bound and upper bound, and then set up the uniform random variable using the random variable constructor for uniform distribution, and just define lower bound and upper bound, and just give it any description that you wish to call it. And then from there, you just consolidate the random data from the prior using the random variable set constructor, the same fashion as what you did in the previous task, and you just make sure that you define the members correctly. In this case, it's just a stiffness because that's the epistemic parameter that we wish to estimate. And from there, you can just consolidate the input prior random variable for the nominal model using the open cosine input constructor. And this is exactly the same. You just use the input constructor, and the members are just basically your random variable set, and the displacement. These are the model inputs. And from there, you can prepare the nominal function handle using the open cosine Mayo constructor, and it's exactly the same as what you did in the deterministic analysis. So everything here remains unchanged. And from there, you can set up the model evaluator by adding the Mayo constructor in the previous step to the open cosine evaluator constructor. So just use this evaluator object, and then you just essentially input this xMayo Bayes as the member. And from there, you can define the nominal model using the open cosine model constructor in similar fashion as what you did previously. So nothing's changed as well. And then after which, you define the log likelihood function, which is the next key ingredient in Bayesian model updating. And you can just simply use the log likelihood constructor, which is described as follows. And you just input this input Bayes and the synthetic data. And then the width factor is where you actually input the standard deviation of the log likelihood, which we set it as 1. So the log likelihood is in essence actually requires only the X model Bayes, which is the nominal model that you just defined, and the synthetic data, which you actually did in a second task when you have to generate the synthetic data using Monte Carlo simulation. In task 4b, we are to then set up the TMCMC sampler, which will be the main sampling technique used to generate samples from the posterior. So we actually set the sample size to be 600, but of course you can always use a different value of samples that you wish to generate from the posterior. And from there, you can then consolidate the prior and likelihood functions using the open cosine Bayesian model updating object. And this is done as follows. And you just need to define your log likelihood and the output names and the number of samples that you wish to generate. From there, you can just apply TMCMC to run the TMCMC sampler. And then from there, you can then obtain the generated samples using TMCMC. So that's all there is for task 4. And finally, we proceed to task 5. So in task 5, we are to analyze the sample outputs, and this is actually one of the most straightforward tasks that we have. So essentially, you just need to plot up the histogram of the samples that you obtain via TMCMC. So in essence, all you need to do is just set up the figure, the histograms and samples TMCMC, and give it a title and the labels, and this generates the histogram of the samples. And if you want, you can also calculate the sample mean and standard deviation and have them all displayed in a command window using this line over here. And from there, you can also calculate the percentage error of the TMC sampler by taking the ratio of the standard deviation and the mean, multiplied it by 100. And you can also choose to display this value in the command window. And then from there, you have to obtain, and then after this is done, you can, if you want to do the comparison between the calibrated model and the synthetic data, you do the following. So first, we need to obtain synthetic data for the output which is the force measurement, and you simply just convert the table output of the synthetic data into an array. So it's essentially you just need to do this, just need to get this, and from there you can just extract the synthetic force measurements that you generated using Monte Carlo simulation. Now, to obtain the output from the calibrated updated model, this is going to be a little bit more involved. So you just need essentially first to obtain the parameters, and you just perform this the following steps over here, as you can see in this from 173 to 182, which I believe that this has been gone through in one of the webinars. So I will not be speaking too much in detail about in this step, but essentially this is how one would to obtain output from the calibrated updated model, and in essence this is actually you putting in the estimated sample outputs from the TMCMC and input it back to the nominal model, and and this is how one could get the calibrated updated model. And from there you can then plot the histogram of the updated model versus the synthetic data. So essentially you just plot the two histograms, you just use the hold on function, and you just plot the synthetic force measurement and updated model output, and from there you can just see and compare the distribution and see if there are any similarities or differences, and you can make comments on it. So without further ado, let's run this code as a whole. But of course, as mentioned, please make sure that your model function handles and your MATLAB files are all in the same directory. So allow me to run the code, but do take note that this might take some time, so this is just a bit of a disclaimer. And there you go. So this is the histogram of the samples that you obtain from the posterior using the TMCMC sampler, and this is the histogram comparison between the histogram profile of synthetic data and that you generate from the updated model. So with that actually concludes the this video over here, and I do hope that we have fun and that we have learned something from this course. And with that, thank you so much for your undivided attention, and have a nice day.